At the time I graduated, there were not a lot of jobs in physics, and there was an opportunity to work at the Stanford Linear Accelerator Center running a group that did research in computer science. And in those days, computer science was not the glamorous field it is today. People would laugh when you said the word computer science. I mean, what kind of science is there in writing computer programs after all? But anyway, it was a fledgling field, and I thought it was interesting. And the area of computer science I was interested in was pattern recognition, which also did have application at SLAC and the data that they had there. And the sort of fashionable technique in pattern recognition of the day, the main journal being the IEEE Transactions on Computers, was nearest neighbor and kernel type techniques were very popular then. And so I was intrigued, but I realized that you couldn't really use them if you use the naive way of trying to find the nearest neighbors. In other words, if you're going to classify a new sample by its nearest neighbor in the training data set, you had to find its nearest neighbor in the training data set, and that meant looking at all the observations in the training data set every time you wanted to do a classification. And in those days, SLAC had what was at that time very large data sets, typically 5, 10, 15,000 observations, which today are not large, but in those days, in the early 70s, was considered very large data sets. And clearly, nearest neighbors were not going to work, were not going to be computationally feasible on data sets of that size unless you did something. So I started thinking about fast algorithms for finding nearest neighbors, because I viewed myself as a computer scientist, certainly not as a statistician. And was working in that, and wrote a paper or two, but then an associate brought me in contact with a very bright young student named John Bentley, who was Don Knuth's student at Stanford. And he had some ideas on nearest neighbors, and I had some ideas, and we started working together on the problem of how do you rapidly find nearest neighbors without having to, every time you wanted to find the nearest neighbor, make a pass over all of the data. And so we came up with an algorithm, and it was a recursive partitioning algorithm based on binary trees. And since you all are familiar with CART, I can tell you in a minute or so what the algorithm was. It simply said you recursively partition, just like CART does now, but at every step you choose the variable that has the largest spread, as measured by its variance or interquartile range or whatever, and then split it at the median. Now, if you recurse this, you would tend to break up the space into rectangular, to the extent you could, before you ran out of data, break up the space into rectangular boxes. And then when you wanted to find the nearest neighbor, you would start at the root of the tree, traverse down to the terminal node that this was in, and then start backtracking and looking to see if you had to explore other branches of the tree depending on how far away your current nearest neighbor was. And so we did that algorithm, and we published it, and people tell me it's still among those of the state of the art today. But my purpose in finding, John was interested in computer science and computational geometry as an end in itself. I was interested in near neighbors because I wanted to do classification. And so I got to thinking, you know, if you know that at the end of the day you're going to be using these nearest neighbors for classification, maybe there's a better way to do the splitting than simply take the largest spread and split at the median. Maybe you should take classification information into account when you decide when to split, if your goal at the end of the day is to do classification. So I started thinking about that, and just like Leo said, all of a sudden, a eureka. One day I was laying in bed in the morning in my usual surrealistic haze when I first wake up, staring at the ceiling, and it hit me. Why not choose the variables at each split that had the most classification information and recurse on that, and then make the tree and then find nearest neighbors in that tree? But then later on I got to thinking, well, if you're doing that, why do you need the nearest neighbors at all? Let's just do a majority vote in the box you end up in. And that's how I came to trees.